On a workbench in Ottawa, technicians at a teardown firm lift the lid off a phone that went on sale with no announcement, no press event, and no leaked benchmark. And underneath that lid sits a single die the size of a fingernail that this video is going to take apart layer by layer, because the deepest layer of this particular die is not the layer the headline settled on in the first week. The path runs from the processor cores on the surface, down through the modem silicon fused beside them, into the memory bonded on top, out to the radio circuits at the edge of the package, and finally into the transistor geometry itself, where the real argument about what this chip proves and what it costs to prove it gets settled. That argument was supposed to be closed in 2019, when an equipment ban tried to keep a chip like this one from ever existing. The same buried fact keeps surfacing at every layer of this die. The equipment restriction that was meant to keep this processor out of existence is the reason its internal layout looks the way it does, and that signature is not a talking point. It is visible in the silicon itself, in the spacing of the metal, in the shape of the modem block, and in the yield economics nobody outside the foundry gets to see. 5 cuts and 1 deep incision will trace that signature from the package lid down to the transistor pitch. The first cut needs no instrument at all. The package opens to reveal a single system in package built around one primary logic die, rather than the traditional arrangement of an application processor, paired with a separately sourced modem chip sitting nearby on the board. That single packaging choice already overturns the assumption most coverage repeated in the first 48 hours after the phone appeared, the assumption that this was simply an older processor reheated and resold. The geometry says otherwise before a single transistor has been measured, because folding the modem into the same die as the application processor removes a separately sourced part that used to be a choke point of its own, and that removal is doing more structural work than any statement about self-reliance a company press release could offer. A modem bought from an outside supplier can be blocked at the border. A modem fused into the same piece of silicon as the rest of the processor cannot be intercepted as a separate shipment because it never travels as one. Moving past the package wall, the next cut exposes the application processor core complex, and it identifies a multi-core arrangement built on the company's own processor core design paired with an in-house graphics block. That pairing is consistent with design work that never stalled even during the years its manufacturing options were under direct restriction, because chip architecture and chip fabrication are 2 separate battles, fought with separate tools on separate timelines. This layer proves the design side kept moving while the process side sat frozen, and the proof shows up in independent benchmark testing of retail units, where the processor's sustained performance trailed the flagship, Silicon released the same year by competing American and European chip makers. That gap is not evidence of a design team that fell behind. It is the predictable signature of a competent design running on an older fabrication process, and the bottleneck this layer reveals sits downstream in the foundry, not upstream in the drafting room where the cores were actually drawn. The third cut exposes the integrated modem block, and the teardown analysis reports a 5th generation capable modem fused into the same silicon as the application processor, the first time this company's flagship line had shipped a domestically produced 5th generation modem since an earlier set of restrictions cut off its prior modem supply roughly 3 years before this device appeared. This is the layer that explains the silence around the launch. There was no marketing event, no spec sheet bragging about wireless speed, because confirming the modem publicly before independent analysts confirmed it themselves would have invited the exact customs and licensing scrutiny the company had spent 3 years trying to avoid. The presence of a working 5th generation modem on this die, after 3 years of shipping phones with no such radio at all, reads less like an announcement and more like a balance sheet quietly closing, the way a business resumes a product line it never officially admitted losing in the first place. Beneath the modem sits the memory and packaging stack, and the analysis places fast mobile memory in close physical proximity to the logic die, using packaging techniques that shorten the distance data has to travel between memory and processor. That shortened distance recovers real-world speed that an older transistor node would otherwise give up, and the choice functions here as a workaround layered directly on top of a manufacturing limitation, not as an independent feature added for its own sake. It also matters because packaging is one of the few places in this supply chain where domestic firms had years of unrestricted practice, since advanced packaging equipment never faced the same blanket controls applied to the lithography tools used for the finest transistor layers. This layer is doing extra work specifically because the layer beneath it cannot do all the work alone, and that division of labor between packaging and process is itself a quiet admission of where the harder constraint actually lives. Around the edge of the die sits the radio frequency periphery, the filters and power amplifiers that have to be qualified together with a new modem before a phone can reliably hold a connection on a commercial 5th-generation network. This outer ring of the package is where a modem on paper becomes a modem that actually keeps a signal in a moving car, and its presence is the quiet proof that the integration was tested as a working system rather than assembled as a demonstration unit for a single press photo. Radio frequency qualification rarely makes it into a launch narrative, but its absence would have been the fastest way for outside observers to expose the modem claim as cosmetic, so the fact that field reports describe ordinary stable network behavior in retail units is itself a data point, even without a formal independent conformance test sitting on the public record. All 5 of those cuts point downward toward the same answer, and the transistor geometry itself is where that answer becomes measurable. Physical analysis attributes the die's manufacture to the country's largest contract chip maker, using a process the analysis characterizes as roughly equivalent to a 7-nanometer-class node produced with deep ultraviolet lithography tools rather than the extreme ultraviolet machines that a Dutch equipment supplier has been barred from selling to that country since 2019. This is the cut the whole dissection has been walking toward, because it is the layer where a trade restriction stops being a policy document and becomes a measurable property of the silicon. The absence of an extreme ultraviolet machine in the room where this wafer was made is written into the transistor pitch itself, and no amount of clever design upstream can erase a constraint that physical. A 7-nanometer-class node has historically required extreme ultraviolet lithography to pattern its finest features in a single exposure, because the wavelength of that light is short enough to draw lines that older, deep ultraviolet light physically cannot resolve in one pass. The chipmaker in question does not have legal access to extreme ultraviolet tools. The 2019 export restriction on those systems, later tightened by additional measures from the United States, kept that entire category of machine out of the country. What the teardown's geometry implies and what the chipmaker has not stated outright in any public claim is that the foundry reached this density by exposing the same layer of the wafer multiple times with deep ultraviolet light, a technique called multi-patterning, redrawing the same fine lines 2 or 3 times instead of once. Multi-patterning is not a secret. It is decades old, and it was standard industry practice everywhere before extreme ultraviolet tools matured enough for production use. But at this density, it turns one manufacturing step into several, and each additional exposure adds equipment time, adds an alignment tolerance the process has to hit correctly on every single pass, and adds defect opportunities that compound with every repeated trip through the lithography bay. This die is not proof that the export ban failed. It is proof of exactly how much that ban cost to route around, expressed in process steps and equipment hours stacked behind every wafer, rather than in a dollar figure printed on an invoice nobody outside the foundry has ever seen. Picture a printing press that can only stamp one color with each pass through the machine. To produce a final image as sharp as a press built for full color in a single stroke, the same page has to run through the machine 3 or 4 times, lined up by hand on every pass, and each extra pass is another chance for the image to smear. That is the physical trade being made on every wafer of this node, and if you wanted to hold that cost difference as an object rather than a percentage, it is the difference between a single printed sheet and the small stack of sheets it actually takes to reproduce that same page by hand, run after run until it resembles the one-pass original. 3 things this dissection cannot settle deserve to be stated plainly rather than waved away. No outside party, including the analysts cited throughout this teardown, has obtained the foundry's actual production yield for this node, so any number circulating about the percentage of usable chips per wafer is an industry estimate, not a disclosed figure, and it belongs in a range rather than treated as fact. The physical evidence for multi-patterning is the consensus interpretation of the geometry and of the foundry's known toolset, not a confirmed process flow the foundry has published itself, which means this dissection is reading the scar tissue of the technique rather than watching the procedure that produced it. And heat and density limits are real physical constraints on how far this approach can scale, because multi-patterning adds cost and complexity fastest precisely at the smallest geometries, which is exactly why the same workaround gets harder rather than easier if this lineage is pushed toward the next node down. Put together, the teardown proves a working, domestically produced 7-nanometer-class chip exists and ships in volume while leaving the exact yield, the exact cost, and the exact scalability of that achievement as open questions that only the foundry's own internal records could ever close. What this single die ultimately proves is narrower than the first week of headlines claimed, and sturdier than the skeptics who dismissed it conceded. It does not show that this country has matched the cutting edge of global chip making. It shows a working substitute for the one specific machine it was denied, paid for in process complexity rather than open market dollars, and built into a product a customer can buy and hold today rather than a lab sample held up for a photograph. Every layer this dissection opened, from the fused modem to the packaging shortcut to the multiplied lithography passes, is the same workaround restated in a different material, and that repetition across independent layers is what turns one teardown into a structural reading rather than a guess. The chip that made the American reference design for a domestic competitor look borrowed did not need to beat that design on every spec. It only needed to exist, on a shelf, without an announcement, while the machine that was supposed to stop it sat exactly where the export rule left it, outside the building. Sanctions did not stop this chip from existing. They decided what this chip would have to look like underneath. If you had the next teardown on this bench, which single piece of hardware would you want opened up first, and why? Subscribe for the next dissection when another object goes under the same blade, and turn on notifications so you do not miss when it drops.